Let's get started with lecture 19. So last time we finished chapter 16. We talked a lot about various properties of traveling waves. But in all the situations we considered so far, we just had one source putting oscillations into a medium and they propagated away. So in general, we can have more complex scenarios where there are multiple sources. So a simple example is, you can take maybe a string that's stretched, and previously we maybe took one end point of it and moved it up and down, and we had these pulses propagating away. But maybe, you do that and then you also grab a point in the middle, move it up and down, so you're going to get some pulses moving away from that point as well, right? So consider this scenario here. So let's say superposition of waves. So suppose you have this stretched string here, and you take this point, move it up and down, so pulse created. Suppose you also take this point, move it up and down, right? So you also create a pulse over there. So what happens, right? So a little bit later, you created a disturbance in the middle, right? So that disturbance typically moves in both directions. It propagates away from the source. So if that point was here, maybe we get something over here that's moving this way. And the same distance over here, we have a similar pulse moving that way. And let's say at the same time we've created a pulse here. So there's going to be another bump, another pulse moving this way in this stretched string. So the question is, what happens when these disturbances hit each other? They end up at the same position. So that's really the essence of this chapter. So let's start with a brief overview of what we'll be talking about. Right. So that's the first thing we'll talk about is the principle of superposition, which is really simple to state. It basically says these disturbances, these displacements, just get added together. The waves, the pulses, the waves go through each other, and the displacement at any point in space will be just a sum of the two displacements from these different pulses. Or if you have, if let's say you're in higher dimensions, you're in 2 dimensions, and you have several sources, they all create these waves that propagate away. Suppose, I don't know, it's raining on a lake, right? These raindrops hit the surface of the water at various points. They create these wave fronts, they propagate away. So at some point on the surface of the water, what is the height relative to the equilibrium position? Turns out for waves that are described by linear equations, so I'm not going into that too much, but basically the idea is if the displacements are not too large, you're in a regime of relatively small displacements, this principle holds and we can just add them. So that's really the essence of this chapter. And then we'll talk about some applications of this. So one application is a standing wave, where every point kind of moves up and down like this. If you look at a standing wave pattern, you see this curved string move down, become flat, go down, the whole thing moves up and down together, for example. And we can make sense of it as a superposition of two traveling waves, one going to the right, one going to the left. So we'll discuss this particular application, which is really important in musical instruments. So typically when you play a musical instrument, maybe you play the guitar, you create a standing wave in the string. Or if you're playing a wind instrument like the flute, again you're creating a standing longitudinal wave in the pressure of the air inside this tube. So we'll talk about that. In standing waves, there are points that just never move. They're called nodes. There are points that have the maximum possible displacement, like these peaks here. They're called antinodes. So we'll talk about standing waves, the mathematics related to them, what happens at the boundary. So we'll specifically consider cases involving strings and sound waves in let's say something like a flute. Yeah, so that's what I was talking about. There are two alternative ways to think about sound waves. So one is in terms of pressure, another is in terms of the actual displacement of molecules. So we talk about these complementary pictures and the associated boundary conditions. Let's say if you have a closed end or you have an open end, what happens to each of these quantities, and what are the standing waves we can get, and what are their frequencies, etc. We talk about more generally the phenomenon of interference, which is again multiple sources creating these wavefronts and they add up. So talk about the mathematics of how they add up and what patterns get generated. So there's going to be certain areas where this interference is destructive, so you get small or zero amplitudes. And that's when one source wants to create a displacement maybe upward, the other one wants to create a displacement downward, and you add a positive and a negative number and they cancel out. And you have constructive interference where they add up and produce a wave with a larger amplitude. We also talk about another application. It's called the phenomenon of beats. So that again can be understood as two sinusoidal waves traveling in the same direction but a slight difference in their frequency. So we talk about the pattern, and there is this emergent frequency for beats that one can hear, where it gets louder with some frequency. And we talk about how to extract it from the actual frequency of these traveling waves. So one application would be, putting two loudspeakers close to each other with a slight difference in the frequency, and then listening to what sound comes out. So it has applications in music, telecommunications, etc. All right. Okay. So the principle of superposition is really one of the fundamental ways waves differ from particles. So if you have two particles, right, so you have two baseball players and they hit the ball. So these two baseballs are moving toward each other. If they hit each other, they just bounce back. They don't go through each other. But if you have two loudspeakers and they create these sound waves, they just go through each other because it's a disturbance in the medium. It's changing, let's say, the pressure of the air. And there are some fundamental equations that govern the propagation of waves, and it turns out that this equation is linear in that object that fluctuates, whether it's the displacement or the pressure or some density or something, or the electric and magnetic field. The idea is if you have one solution corresponding to a wave generated from one source, and you have another solution, the sum of these solutions will also satisfy all the laws of nature that gave rise to these individual waves. And a consequence of that is the principle of superposition, which is basically if you have, let's say, a displacement d1, so suppose wave 1 displaces a particle in the medium by d1, wave 2 simultaneously displaces it by d2, the net displacement of the particle is d1 plus d2. Right? So that's a key concept of this chapter, and most of what we will be doing is to explore the consequences of this simple principle. All right, so let's consider two pulses. So I have one pulse that looks like this, a triangular pulse, for example, moving this way, moving to the right, and then there's another pulse that looks like that, so a triangle, and then another triangle, let's say. And this moves to the left. Okay, so they're both moving toward each other. So before they reach each other, you know, a little bit later, maybe this will be here, this will be over here, right? And then at some point they will be on top of each other, right? So they will be at the same position in space. All right, so let's consider, I don't know, let's say this pulse is moved by some amount so that, you know, let's say that the up triangles are overlapping. So what would we see? Well, it's going to be somewhere over here, right? So this triangle that's moving this way will look like this. And this triangle will look like that at the same position. And we have this other triangle trailing, and these move this way. So if I want to draw the snapshot figure over here, well, in this region, there's just one of them. So it's, let's say it's D2 and D1 is 0. So it gets added to nothing. So I have that triangle. But here I have these two similar triangles. So if you add them together, you're going to get a triangle that has double the height, right? So somehow this displacement changes. And the width have to be the same. So let me try to draw it better. So that has the same width, half the height, you know, we're gonna get something like this. So then a little bit later, again, you know, if you have maybe this up triangle overlapping the down triangle here, so what are the things we're gonna see? We're gonna see this up triangle moving to the right here, and the left mover will look like that. So if you draw the snapshot figure, in this region you just see an up triangle from this one that's moving to the left, and then in this region they just cancel, right? So we're going to get this small pulse. And then once they go through each other, they look like themselves, and they've just passed through each other without any changes. So that's a consequence of the principle of superposition. So that's a better picture of the same two pulses with some numbers put in. And yeah, so we can have like constructive when they get added and they have the same sign, and we can have destructive interference, they added and they have opposite signs, so they just flatten out. All right, so here's a quick question. So pause the video, try to figure out the answer. All right. So we have two pulses on a string. They approach each other at speeds 1 meter per second. So at t equal 3 seconds, okay? So at t equal 3, that's at t equal 0. So 3 seconds later, this triangle that's between 0 and 2 will have moved forward by 3 meters. So it will be between 3 and 5. It will be over here, right? And the one that's, and the rectangle that's between 6 and 8 moves to the left by 3 meters, so it will be between, again, 3 and 5. So if you add them, we're just adding this constant height of the rectangular pulse to the triangle, so it just shifts up the triangle, and then C must be the correct answer. So basically, getting the snapshot figure at a given time, if you have these multiple pulses that are traveling, we just figure out what they look like, what each of them looks like at the time we're interested in, and then we add them, and that's it, and that gives us the snapshot figure. This is direct application of the principle of superposition. All right, how about this one? Again, pause the video, try to visualize what's happening here. All right, so now we have this downward triangle, upward rectangular pulse. Again, after 3 seconds, the triangle will be between 3 and 5. This rectangular pulse will be between 3 and 5. But this is positive, this is negative. So it's basically like shifting again this downward triangle up, right, by this amount when you add them together. So for example, here we're going to get 0. In the middle, again, we're going to get 0. And in between, it must be just this line shifted up. So by just adding them, we find that B is the correct answer here. All right. So this is a photograph, a time-lapse photograph. So a whole bunch of snapshot figures of a standing wave on a vibrating string. So what is happening? So basically you have this pattern, right? And the whole pattern kind of gets flatter, goes down, goes up, right? Just looking at it, it doesn't look like anything is traveling. It's not very easy to see the superposition of two waves moving in the opposite direction. But it's just simple trigonometry to figure out what happens. So we can just start the other way. We can get two sinusoidal waves traveling in the opposite directions and figure out, what's the superposition pattern that gets generated, right? So standing wave from two sine waves. Okay. So let's say I have wave 1 that looks like this. And is moving this way. And let's say we have wave 2 that, let's say at time 0 they look, maybe it looks the opposite, so let me just shift it this way. Okay, and it's moving this way. right, so at time t equals 0, so let's say that's wave 2. All right, so what is the superposition here? Well, at every point in time, this is the negative of that, so it's going to be flat. Let's say this is t equal 0. Okay. So now what happens when, let's say, a quarter of a period has passed, right? So after a quarter of a period, this guy moves over here, right? The period is from here to here, right? So a quarter of it is that distance. Well, I mean, that's a quarter of the wavelength, and it's moving at speed v, right? So because lambda is v times the period, then over a quarter of a period, it moves by a quarter of the wavelength. So this wave will be here. Yeah, so when it's 0, it will have a maximum. At the maximum, it will come to 0. This 0, it will be the minimum. At this minimum, it will be 0. Here again, maximum, 0. Minimum, 0. And then maximum. Okay, so that's this one that's moving this way. The other one, the blue one, that's moving this way. So again, if it moves by a quarter of the wavelength, see, this point shifts over here, right? And then the pattern repeats itself, so it will be identical to this. And therefore the red curve now at t equal capital T over 4 will look like something like this. It's just double the amplitude. Okay. So now imagine a little bit of time has passed, some small time delta t. So let's see. So this wave that's here, right, it looks like this. Maybe it shifted just a little bit this way. So the 0 will shift this way, this 0 will shift this way. So I won't draw the whole thing, right? A little bit later, this wave 1 will be over here. Wave 2, which was again here, looked like this, will be over here. So it goes from here to here, let's say. Okay. Now let's maybe continue this. So something interesting happens now. See, this point that has 0 amplitude, it seems that it remains at 0 amplitude, right? Because it's this height, which is negative, plus this height, which is positive, and if they look the same, we shift them by the same amount, those are going to be the same heights. So that's interesting. So it seems the pattern is that we're going to get these nodes, right? And basically now, a little bit later, again, this one will be a node as well. Now what happens is that the superposition kind of goes up and comes down, but it's not going to go all the way to this maximum amplitude. It will be something like this. It will be a little bit flatter. So let's say t equal t over 4 plus delta t small, corresponding to that displacement. Again, the nodes will stay the same, right? The places where the displacement is 0. And now somehow we have a smaller amplitude. So that's really the fate of this, right? So you have this thing and then it becomes flat and then later it goes down and then goes down all the way to this maximum amplitude, then begins to come back up again. So the idea is we're going to get this fixed envelope here. Envelope. Something like this, so the maximum. And then every point, performs harmonic oscillation up and down up to that fixed envelope. So here there are these points right in the middle of the nodes that have the maximum amplitude. And that's really what a standing wave is. Okay, so let's go back, try to see these pictures a little bit better. It helps to draw these by hand, because staring at a figure may be quite confusing. But once we do it once, we can have a good sense of what is happening. So here they're all on top of each. They're all drawn together. So we have the red wave traveling to the right, green is traveling to the left, and then the blue is the superposition. So at some point in time, it looks like that. And when they overlap exactly, you're going to get this maximum amplitude, and then it's coming down. But the point is, the nodes, the places where the displacement is 0, they remain the same. All right, so that's that line. That line is a nodal line, right? So here the amplitude is 0, 0, 0, 0, 0. And here you have a maximum amplitude in all of them. So that's called an antinode, right in the middle of them. Okay, so let's think about the distances, right, between the nodes. So the statement is that the distances between two consecutive nodes is lambda over 2. Right? How do we figure it out? Well, it's kind of easy, right? So these are, one lambda is from here to here, and then two nodes appear here and here. So anywhere where you get these zeros, which happens twice in one wavelength, that's a node, and then the distance between them is just lambda over 2, the wavelength of the original individual waves, wave 1 and wave 2, divided by 2. So now this distance here is lambda over 2, where this distance, the wavelength of the original wave, is lambda. And if the amplitude of the original wave is A, the maximum amplitude for the envelope from here to here is 2A, right? Because they look identical right here, and they just add up, so we're going to get twice the amplitude of the oscillations. Okay, so that's our picture. And the antinodal points are exactly halfway between the nodes. So if you think about the intensity, we know that the intensity is proportional to amplitude squared, right? So that this envelope here is really an envelope for the amplitude for the oscillation at any point. So therefore we have zero intensity at the nodal points and the maximum intensity at the antinodal points. Okay. So this is a quick question. So pause the video, try to figure out the answer. So we know that the distance between the nodes is lambda over 2. So this is one node, this is the next one. So what is the distance? Well, this seems to be 0.25. This seems to be 0.75. So that distance seems to be half a meter. And twice that is 1 meter, right? We could also think about the distance from one antinode to the next, again because they're shifted. That's again is lambda over 2, so that's 0 to 0.5, and twice that is 1 meter. So let's now think a little bit about the mathematics of these standing waves. So let's consider one sinusoidal wave traveling to the right. So let's say this is let's call the amplitude small a. Then we have sine kx minus omega t. So this is moving this way. So if that's the snapshot at t equals 0, phi naught can be 0. I mean, we can pick the origin in a place such that phi naught is 0. The phase constant is 0. And then we can have a left mover. So let's say the left of x and t. And the only thing that happens is we need to change the sign of the speed. So that changes the sign of omega here. So that's sine kx plus omega t. And that's moving to the left. So again, looks the same, but is moving this way. Again, as a reminder, again, k is 2 pi over lambda. Omega is 2 pi over t, the period, for example. All right? And lambda is v t, so from here one can find that 1 over t is v over lambda. So therefore this right mover is a function of x minus vt, right? And the left mover similarly is a function of x plus vt. Okay. Now, so if we add them, we have the expression, so therefore d of x and t, the superposition that we get from adding these counter-propagating sinusoidal waves with the same amplitude, same wavelength, and same frequency, or same period, becomes a sine kx minus omega t plus sine kx plus omega t. All right. Now, if you remember, sine of, let's say, x plus y is sine x cosine y plus cosine x sine y, right? So using this trig identity, we find sine of kx minus omega t is sine kx cosine of minus omega t, which is the same as cosine of omega t, then plus cosine of kx times sine of minus omega t, which is minus sine of omega t. And similarly, the other term, sine of kx plus omega t, becomes sine kx cosine omega t plus cosine kx sine omega t. So if I add them, I find that d of x and t, see, these terms cancel out, and these terms are the same, so they give me a factor of 2. So that's going to be 2a sine kx cosine omega t. K is inside the parentheses here. So at every point we can imagine this thing to be an amplitude that depends on x, right? And then we perform this simple harmonic motion with frequency omega. So if you plot, let's say, the amplitude sine of kx, well, or let's say this is x, this is a of x. So it's going to go to a maximum, let's say 2a, and the minimum will be minus 2a. And it does this thing, right? And the wavelength is, again, from here to here, we have lambda. That's the wavelength. Right, so that's basically what we derived. Yeah, we have this position-dependent amplitude, and its maximum is, of course, 2a, twice the amplitude of the components, the two traveling waves that make up this standing wave. And yeah, so that's just the math of how this pattern emerges. And we also see from this expression that the nodes don't change, right? Because ultimately your d of x and t factorizes into a function of position and a function of time. And if the function of position has some places where it's 0, which is here, these nodes, then that 0 at every time multiplies some function of time and it remains 0. All right, so here's an example. Let's read it together. So we have a long string, linear density 5 grams per meter, stretched. We know the tension. We know the frequency and amplitude of the waves that are generated at the two ends. So first question, what is the node spacing along the resulting standing wave? And then what is the maximum displacement of the string? All right, so straightforward problem. So try to pause the video, work it out, and then come back and we'll look at the solution together. Okay, so yeah. So what we have is the linear mass density and tension. Immediately that gives us the speed of propagation. We also know the frequency. So knowing the frequency and the speed of propagation, we can find lambda, the wavelength. And we know that the node spacing, the distance between nodes, is half of lambda. All right? So example 17.1. So we know the frequency, we know the tension and mu, so we know that v, the speed of propagation, is the square root of tension over mu. And lambda is v over f. It's v times the period, right? And that's v over f. So node spacing is 1/2 v over f. All right, so what is v? Eight over 5 grams per meter. So that's going to be, yeah, let's just look at the numbers here. So that's the picture. Yeah, 8 over 0.005, so that becomes 40 meters per second. We find lambda, just the speed divided by the frequency, and the spacing is half of it, which is 2 centimeters. And the maximum displacement is just twice the amplitude. So the amplitude was given, it's 2 millimeters. This is twice that. So let's just write that also in the notes. So A max is, so this is part A. Part B is A max is simply twice A. All right. So previously we talked a little bit about waves going across interfaces when the medium changes, when the density, for example, changes in this case. So we argued that the frequency should not change, and therefore, and the speed changes, so the wavelength should change accordingly. Now, it turns out that there's more to this story, right? So when you have some pulse or some wave incident on an interface, like here, you have a pulse traveling along the thicker rope and it hits the interface with the thinner rope. What happens is some of it gets transmitted, some of it goes through, and some of it always gets reflected. Right. So there are two cases where we have to consider the reflections separately. So it turns out when the next medium, so the medium you're incident upon, has a higher speed, string with faster wave speed, which is the case if its density is lower, right? Remember, the speed was the square root of tension over linear mass density. So smaller linear mass density means less inertia, means faster speed. Then the wavelength just gets reflected. The pulse just gets reflected. It kind of looks similar. So if it's a pulse that's upward like that, it gets reflected as an upward pulse like this. But something interesting happens. If your speed decreases on the other side, the wave or the pulse that's reflected is also inverted. So you have this upward pulse reaching that interface. It gets reflected as a downward pulse, something like this. This is a consequence of trying to satisfy, all the equations that govern the dynamics of the boundary conditions, like requiring that this point that belongs both to this medium and the other medium kind of has the same motion. They're moving together. So we're not going into a detailed derivation of this, but it's a result that's quite important to remember. So then this reflection, when you have this type of inversion, we can think about it in terms of a pi shift, a phase shift of pi. The reason is sine of any angle plus pi, if you have some angle theta here, that's the sine, and cosine, and that's the cosine. If you add a pi, you go over here, so both the sine and cosine change sign. So the inversion means the displacements kind of go to negative what they were, right? And we can take that into account by adding a phase shift of pi 180 degrees to the phase of the traveling wave. All right. So an extreme case of a second medium where the speed goes down is like you have a hard boundary, right? That point doesn't move, it's fixed, it's attached to the wall, nothing can go through, it's really high density. So if a pulse goes and hits this wall, the entire thing gets reflected and comes back. Let's take a look at this in our simulation. So I can generate a pulse, right? It's traveling, and then it reaches this point, and then that point is fixed. So because it's fixed, it pulls these bees down and causes this inversion of the pulse. Let's look at a continuous oscillation here. So let's see what happens now. So yeah, so that point remains as a node, and we can get these complex patterns after many reflections. Okay, so let's stop here, and we'll continue our discussion in the next lecture.